Okay, we're going to think about the kind of projection that goes on when we work with regression models. So instead of thinking about a pair of variables y and x, 2 and 3, and a pair of variables y and x, 3 and 2, and 4 and 3, we're going to think instead about a vector of y variables, a vector of x variables, and we are also going to talk about an intercept, a column vector of variables values fixed equal to 1. So we can attempt to visualize this on the plot. We want 1, 1 and 1. So to try and attempt to make some sense of what's going on in the 3 dimensions we're working with here, that's going to define the far end of that box. So let's draw in the vector as such. So this is the vector x1. Next we want to write the second x vector, and we said here we have something that's equal to 3 and it contains 2 and another 3. So as an attempt to illustrate this, that's going to define a box looking something like this, and we'll now draw the vector in, and that's going to go to here. Now the first idea is we're going to multiply x1 and x2 by a constant term b1 and b2. So b1 multiplied by x can give us a point further. It could be negative, it could be less than 1. Likewise, b2 is going to define any kind of multiplication of that vector, and if we add the two together, we have essentially defined some kind of, it looks a lot like a plane. Possibly shouldn't call it a plane, but it looks a lot like a plane. So b1 x1 plus b2 x2 for unknown values of b is going to define something on that plane. So now let's look at this y vector, which we said is a 2 and a 3, and it extends to 4. So we have some kind of vector defined here, and we'll plot that vector. So we have y here. Now all our interest is in terms of finding, and we are thinking about the distance between this vector y and a point on this, what I'm going to call plane, but otherwise we're going to think of as y hat. And some of the things that emerge from thinking about this are that if we want to minimize this distance here, then out of all the vectors we can have here that minimize this distance, the only ones that are going to do the job of minimizing it have to be essentially orthogonal to that, what we're calling a plane. So that's a way of thinking about regression in terms of a vector outlay. And this is interesting. It tells us a lot of things. It tells us that this vector that we're trying to minimize the sum of squared residuals. If we do that, it has to be orthogonal to anything contained here. So anything that's orthogonal to a column vector containing 1, 1 and 1 is going to equal 0. So our vector of residuals E is going to sum to 0 or have mean 0 because of this construction. It's going to have mean 0 because it's orthogonal to a column vector containing 1s. Nothing in here about assuming anything on this vector of residuals. In minimizing the length of that vector, we have to have something that's orthogonal to these x terms, so this has to have mean 0. It also means it can't be independent, because clearly once I know two values, the third value of my vector of residuals is fixed, and the more terms I add, the less freedom there is to choose values.